Welcome to This Explainer. Today, we're diving into the absolute bedrock of how we understand the universe. Think about it. Every single thing we know about physics, every grand theory, every complex model, every fundamental law is built entirely on our ability to observe, measure, and record the physical world around us. But how do we actually know our measurements are right? How do we communicate them so that a researcher in Tokyo understands exactly what a scientist in London is seeing? And what happens when our imperfect, everyday human tools inevitably introduce errors? Today, we are going on the journey of a measurement.
To get us there, here is our roadmap for today. We're going to start with the language of physics, diving into units and scales. Then, we'll validate our math in balancing the equation, confront the messy physical reality of our tools in the truth in measurement, learn the actual rules for combining uncertainties, and finally, we'll add the crucial element of direction. All right, let's jump straight into Chapter 1, the language of physics. Imagine someone tells you they can run 1,500 in 200 seconds. Are they fast or are they incredibly slow? Well, if they mean 1,500 meters, they are absolutely flying. But if they mean 1,500 centimeters, yeah, they're barely moving at all. You see, a numerical value all by itself is completely meaningless in physics. Every physical quantity requires both a number and a unit to make any sense.
And the thing is, physics deals with the unimaginably tiny and the incomprehensibly massive. Because of this extreme range, physicists rely heavily on orders of magnitude, which are basically powers of 10, to quickly estimate and compare wildly different sizes. If you know the rough mass of a typical boy, you can reasonably step up a couple of orders of magnitude to estimate the mass of an elephant. And from that elephant, you can step up another order of magnitude to estimate the mass of a jumbo jet. This ability to quickly estimate is a huge deal. It gives us a built-in reality check when we're working through really complex problems.
Let me give you a number to really hammer home why we need this kind of scientific notation. Imagine a 1 followed by 61 zeros, 10 to the power of 61. That staggering number is the difference in mass between our sun and a single tiny electron. If we actually tried to write that out in standard numbers every single time we did an astrophysics calculation, we'd literally run out of paper, not to mention patience. Scientific notation keeps our mathematical language incredibly clean and precise.
Now, to actually communicate across these mind-boggling scales, we need a universal alphabet. And that's exactly what the SI base units provide. Whether you're measuring the massive thrust of a Saturn V rocket or the subtle heat of a chemical reaction, all physical measurements eventually boil right down to these fundamental units: the kilogram, the meter, the second, the ampere, and the Kelvin. This is the universal language that unites scientists all around the globe.
Moving right along, let's head into Part 2, balancing the equation. Now that we have our universal alphabet, how do we make sure we're writing sensible sentences? This is where we validate our measurements and ensure our mathematical formulas actually reflect physical reality. I absolutely love this quote from our source material because it perfectly simply captures the concept of equation homogeneity. Look, you can easily figure out the total number of oranges in 2 bags if one has 3 and the other has 4. But it is total nonsense to add 3 oranges to 4 mangoes and expect to get a meaningful single number at the end. It just doesn't work. In physics, the rule is strict. You can only add, subtract, or equate terms if they share the exact same base units.
Let's actually see this in action with a classic kinematics equation, v equals u plus at. Final velocity equals initial velocity plus acceleration multiplied by time. For this equation to actually be valid, it has to be homogeneous. So let's break it down and check it. Final velocity, v, is measured in meters per second. Initial velocity, u, is also meters per second. So far, so good. Now, what about that at term at the end? Acceleration is meters per second squared, and we're multiplying that by time, which is just seconds. One of those seconds cancels out, leaving us with, you guessed it, meters per second. All 3 terms match perfectly. The equation is completely balanced.
Okay, so our math checks out on the whiteboard. But what happens when we take those perfectly balanced equations out into the messy, unpredictable real world? That brings us to Section 3. The truth in measurement. And the hard truth we have to face is that no measurement is ever perfectly absolute. The reality is, every single instrument we use has a built-in limit. If you need to measure the diameter of a human hair, grabbing a standard school ruler is totally useless. Its uncertainty of plus or minus 1 millimeter is actually larger than the hair itself. For a job like that, you need a specialized instrument, like a micrometer screw gauge, which can measure all the way down to the nearest 1/100th of a millimeter. The instrument you choose entirely dictates the significant figures and the fundamental uncertainty of your data.
And this brings us to a massive misconception that trips up a lot of people: accuracy versus precision.
You hear them used interchangeably all the time, but in physics they are not the same thing. Precision is strictly about how close a set of measured values are to each other. If you measure a copper wire 5 times and get the exact same reading every single time, your results are highly precise. But accuracy? Accuracy is about how close that measured value is to the true, real-world value. You could have a beautifully precise set of readings that are completely and utterly inaccurate just because your instrument was fundamentally flawed or calibrated wrong.
So where do these flaws actually come from? Well, errors basically fall into 2 camps. First, you have systematic errors, which are a fixed shift in one direction. Imagine using an old wooden ruler where the 0 mark has literally been worn away over the years. Every single measurement you take with it is going to be too long by the exact same amount. That's a consistent hardware issue. Random errors, on the other hand, just scatter your readings unpredictably. This is usually the human element, like reading a dial from slightly different angles each time, which we call parallax error, or the tiny, unavoidable fluctuations in your reaction time when you click a stopwatch.
Now, because every single measurement has this inherent error, we run into a compounding problem when we start plugging multiple measurements into our formulas. And that is exactly why we need to master Section 4, combining uncertainties.
Luckily, there are really just 2 golden rules for propagating these errors. If you are adding or subtracting 2 measurements, it's simple. You just add their absolute uncertainties together. But if you're multiplying or dividing values, like, say, calculating the volume of a cylinder by multiplying its length and its area, you have to add their percentage uncertainties together instead. And listen, here is a fascinating trap that catches a lot of physicists out. If you subtract 2 quantities that are very close in value, their absolute errors still add up. That means the resulting tiny number is going to have a massive, sometimes totally unacceptable percentage error. It's a great reminder that we always have to be extremely vigilant about how our errors are interacting.
All right, we've got our units, we've balanced our equations, and we know our error margins. Now we introduce the final piece of the measurement puzzle in Section 5, Direction Matters.
Look, some physical quantities are pretty straightforward. Mass, temperature, they just need a size and a unit. We call those scalar quantities. But if I tell you a car is driving 100 kilometers an hour, you don't actually know where it's going to end up unless I also tell you which way it's going. That is a vector quantity. Vectors have magnitude, a unit, and a specific direction. We're talking about things like velocity, force, and momentum. And the tricky part? Because they have direction, you cannot just simply add them together like regular scalar numbers.
Let's build this out in the real world. If 2 people push a heavy box in the exact same direction, their force vectors add together perfectly. If they push directly against each other, they subtract. But what happens if they push at weird angles? Imagine a ship trying its best to travel due north at 12 kilometers per hour, but a strong river current is pushing it east at 4 kilometers per hour. To figure out where that ship actually ends up, we can't just add 12 and 4. We have to literally draw a vector triangle and use trigonometry to find the combined resultant path. The physical world very rarely operates in perfect, convenient straight lines.
And this exact process works in reverse, too. It's called vector resolution. Imagine a glider being pulled through the air by a tow aircraft. The tow cable is sitting at a 25-degree angle to the horizontal, pulling with a single diagonal force of 620 newtons. But gravity is acting straight down, and drag is acting horizontally backwards. So to actually understand how the glider is flying, physicists use trigonometry to split that single 620 Newton diagonal vector into 2 distinct manageable components, the horizontal force pulling the glider forward and the vertical force lifting its nose up into the air.
Well, we have definitely covered a lot of ground today. But as we wrap up, I want to leave you with this final, somewhat provocative thought. How does acknowledging the fundamental uncertainties and imperfections in our physical world actually make our scientific understanding stronger? It's a profound idea. By rigorously defining our units, perfectly balancing our equations, and ruthlessly calculating our errors and uncertainties, we are not admitting defeat. Far from it. We are actually building a much more honest, incredibly precise, and incredibly powerful model of the universe. Thank you so much for joining me on this journey through the language of physics. Keep questioning, keep measuring, and I'll catch you in the next explainer.